Good morning, students. Last class we discussed about the sag on overhead transmission line. Means the conductor will be fitted in between two level supporters, that may be a equal level supporters or unequal level supporters. Whatever it may be, we have to calculate the sag. So three different cases: equal level supporters, unequal level supporters, and effect of wind and ice. And what are this stringing chart, and also what are the sag template, and what are the advantages, disadvantages, and what is the minimum clearance between the ground and conductor, and for different voltage levels are also clearly shown in the last class. Now I go for the numerical problems on insulators. So generally, first of all, you have to calculate the different voltages at every disk, voltage distribution across at every disk, and also total voltage across the string. Then, so it may be calculated the string efficiency also. So very important for problem wise. So insulator problems are very important as J2 pattern point of view as well as competition point of view also. In JP, Genco, Transco, or it may be a gate examination point of view also. They are asking sometimes. So calculate the topmost conductor voltage, otherwise calculate the string efficiency. Like that they are asking. So let us go through the insulator problems. So go for the insulator problems. Let us identify, otherwise let us remember some of the important points on by considering the insulators. So while solving the insulator problems, that is string efficiency problems, the following points must be kept in mind or must be have to remember. First of all, maximum voltage appear across the disk is nothing but nearest to the conductor. So it may be a, suppose 3 number of disk will be there, third disk having maximum voltage, that is nothing but V3 is the maximum. Suppose 4 disks, V4 is the maximum voltage. Suppose 5 disks are there, V5, that is nothing but voltage across the 5th disk is maximum. Simple say that the maximum voltage appear across the disk nearest to the conductor. It may be 3 insulators, 4 insulators, 5 insulators, whatever it may be. So next one, the voltage across the string is nothing but phase voltage, not a line voltage. So it is a phase voltage. Voltage across the string is nothing but voltage between line and earth. That is nothing but, so phase voltage. Line to earth is nothing but phase voltage. Suppose you have to calculate the line voltage, √3 into, so voltage across the string, that is nothing but √3 into phase voltage. We are getting the line voltage, right? Let us go to the first problem. In a 33 kV overhead line, there are 3 units in the string of insulators. If the capacitance between each insulator pin and earth is 11% of self-capacitance of each insulator, find the first one, distribution of voltage over 3 insulators. Second one, string efficiency. 33 kV overhead transmission line, right? That is the line voltage, 33 kV. We're getting the phase voltage 33 by √3. So that is the V phase, 33 by √3. Some value will be coming. Later we discussed. Now 3 units of string of insulators. That means 3 disks are there. So V1, we have to calculate V1, V2, V3. And total voltage across the string is nothing but V1 plus V2 plus V3. Right? Next. So this is the most important. If the capacitance between each insulator pin and earth is 11% of the self capacitance, that is nothing but K. K is the shunt capacitance by self capacitance, that is nothing but, so 11%, 11 by 100, that is 0.11. K value is 0.11. That's that you have to calculate the string efficiency and voltage across each and every disk. So let us look at the picture. 3 disks are considered as 3 self capacitances C. These three capacitances will resembles the three disc insulators. So this is the nearest to the conductor, that is topmost I1, second one I2, third one I3, right? Now what this one? Phase to earth, this is shunt capacitance Kc. So now we have to identify the three currents I3, then I2, I1. Voltage across first disk V1, voltage across second disk V2, voltage across third disk V3. Now total voltage V is equal to V1 plus V2 plus V3, right? So let us first of all we have to apply. So this one V1, V2, V3 be the voltage across the top, middle and bottom unit respectively, and C is the self capacitance, right, of each unit, and Kc is the shunt capacitance. So K is equal to shunt capacitance by self capacitance. So shunt capacitance is the 11% of self, that is nothing but shunt capacitance is equal to 11% of self capacitance. So shunt capacitance by self capacitance is equal to 11%, that is 11 by 100, that is equal to 0.11. So K is equal to 0.11, and voltage across the string V is equal to the given line voltage 33 kV by root 3. So 33 by root 3 is equal to 19.05 kV. So determine the K value. We determine the voltage across the string, phase voltage. So next, apply KCL at junction A. Look at the figure once again. At junction A, apply KCL. What is the KCL? So at a junction, sum of incoming currents is equal to the sum of outgoing currents. Otherwise, algebraic sum of currents in a junction equal to 0. So look at the apply KCL at junction A. From junction A, small I1, capital I1 are outgoing, and capital I2 is incoming. Therefore, capital I2 is equal to capital I1 plus small I1. So junction A, capital I2 is equal to capital I1 plus small I1. We know the charging current formula, already discussed in the second unit, performance of a transmission line. V by XC. XC is nothing but 1 by omega C. That is V omega C. But this is I2. That's why V2 omega C. Then I1, similarly V1 omega C plus small I1 V1. So small I1 is nothing but shunt capacitance. That's why in place of C, Kc is coming. So V1 K omega C. So take a common factor of omega C and cancel to each other. Then V2 is equal to V1 into 1 plus K. We know the K value, that is 0.11. So V1 into 1 plus 0.11, that is V2 is equal to 1.11 V1. So taken as equation 1. Next, apply KCL at junction B as usual. Incoming current is I3, outgoing current is I2 small I2. So I3 is equal to capital I2 plus small I2. So look at the figure once again, so don't confuse. Capital I3 is the incoming current, and capital I2 and small I2 is the outgoing currents. That's why capital I3 is equal to capital I2 plus small I2. So I3 as usual, charging current, that is V3 by 1 by omega C, that is V3 into omega C, that is equal to V2 into omega C plus what about I2? Small I2 is nothing but, so look at the figure once again. Small I2 is a combination of these two, I1 plus I2. That's why taken as small I2 is equal to V1 plus V2 into K omega C. So look at the figure, don't confuse. Small I1, that is nothing but voltage across this one is V1 only. But coming to small I2, voltage across this one is nothing but combination of these two, V1 plus V2 into K omega C. So don't confuse. Suppose next one, I3 is nothing but V1 plus V2 plus V3. So V1 plus V2 K omega C, once again taken as common factor omega C and cancel to each other. V3 is equal to V2 plus V1 plus V2 K. and substitute V2 value and K value, and we are getting V3 is equal to 1.342 V1. 1.342 V1. We know the V1 value. We know the V2. We know the V3. Now, total voltage. First one, voltage across the whole string. Otherwise, voltage across the string. V is equal to V1 plus V2 plus V3. V1 taken as same plus V2 1.342 V1. Sorry, 1.111 V1 plus V3 1.342 V1. Now adding, so 3.452 V1. And what about V? Phase to neutral voltage 19.05, 33 kV by root 3, 19.05 kV, that is equal to 3.452 V1. So V1 voltage across the topmost unit V1 is equal to 19.05 by 3.452, that is equal to 5.52 kV. So voltage across the topmost unit is 5.52 kV. Now voltage across the middle unit V2, we know the relation. V2 is equal to 1.11 V1. We know the V1 value. 1.11 into 5.52, that is 6.13 kV. As usual, voltage across the bottom unit or voltage across the nearer to the conductor, that is V3. V3 is equal to 1.342 V1, that is 1.342 into 5.52, 7.4 kV. So please observe the voltage distribution over suspension insulator. That is 3 insulators are there. That's why we have 3 voltages V1, V2, V3. So V1 is less than, V2 is less than V3. Otherwise V3 is greater than, V2 is greater than V1. That means V3 is a higher value compared to remaining 2 values. That means the voltage across, maximum voltage appear across the nearer to the conductor. And last one, string efficiency. String efficiency is equal to voltage across the string divided by number of insulators multiplied by topmost unit, I mean disk nearer to the conductor, that is V3. Voltage across the string, that is 19.05 divided by number of insulators 3 into V3 value 7.4. So into 100, that is 85.8%. So string efficiency is 85.8%. Like that, we have to calculate the voltage across each unit and also string efficiency. Now go for the second problem. A 3-phase transmission line is being supported by 3 disc insulators. Again, they given 3 insulators. The potential across top unit, that is nearer to the tower, not the conductor. The potential across the top unit, that is nothing but nearer to the tower or cross arm, but not conductor, right? So that is V1. And middle unit are 8 kV and 11 kV respectively. They are given in problem V1 and V2. V1 is equal to, here 3 discs are there, that is 3 voltages are there, V1, V2, V1, V2, V3. They given V1, V2, but not given V3, right? Now calculate the ratio of capacitance between the pin and earth to self capacitance of each unit, that is K value. Second one, line voltage. Then third one, string efficiency, right? As usual, given data, V1 is equal to 8 kV, V2 is equal to 11 kV. Now let us consider K is equal to ratio of self capacitance by shunt capacitance, right? So apply as usual Kirchhoff current law at junction A. So I2 is equal to I1 plus small I1. That is as usual V2 is equal to V1 into 1 plus K. Suppose we have to remember this equation. V2 is equal to V1 into 1 plus K. Directly we have to put, there is no problem. V2 is equal to, suppose they are given 3 discs and V2 is equal to V1 into 1 plus K directly. They give, we know the V2 value, we know the V1 value. Therefore, so K is equal to V2 minus V1 by V1. That is V2 11 minus 8 by 8, that is 0.375. So K value is ratio of self capacitance to shunt capacitance is 0.375, and already we have to determine the, with the help of given 2 respective voltages, that is V1 and V2. Then apply Kirchhoff current law at junction B. That is nothing but I3 is equal to I2 plus small I2 as usual. So V3 is equal to V2 plus into V1 plus V2 into K. We know the K value 0.375 and determine the, so they already known the V1 and V2 values. V1 is 8 kV, V2 is 11 kV, that is 11 plus 8 plus 11 into K 0.375. We are getting V3 is equal to 18.12 kV. We know they given V1 value, they given V2 value, and we have determined K value and also determined V3. So simple, completed. The voltage between line and earth, that is V1 plus V2 plus V3, that is 8 plus 11 plus 18.12. So 37.12 kV. This is the phase voltage, right? Voltage across the string is nothing but phase voltage. Suppose we have to calculate the line voltage with multiplied by root 3 with phase voltage, that is root 3 into 37.12 kV, that is equal to 64.28 kV, right? We know the voltage across the string, we know the number of discs, we know the voltage across the nearest to the conductor. Then calculate the string efficiency. String efficiency is equal to voltage across the string divided by number of discs or number of insulators multiplied by, so the voltage across the disc nearer to the conductor, that is nothing but V3. So voltage across the string is nothing but we have to put only phase value, not line value. Remember, please, to calculate the string efficiency, we have to utilize phase values. Suppose they calculate line voltage, then only you can multiply with root 3. So voltage across the string is nothing but 37.12 divided by number of insulators 3 into, so V3 value, that is 18.12 multiplied by 100, that is equal to 68.28 percentile, right? And first, so please observe the problems. First problem, they given K value and then you have to determine V1, V2, V3 individually, then string efficiency. But coming to the second problem, they given V1, V2 values, they don't given K value. So by using that V1, V2 values, we have to determine K value, then determine V3, then determine total voltage across the string in phase values and line values, and lastly, we have to determine the string efficiency. Very easy problems. So please look at the problems clearly. So number 3, each line of a 3-phase system is suspended by a string of 3 similar insulators. Again, they given 3 insulators. Most of the times they given 3 insulators, sometimes 4, rarely they given 5, right? So 3 insulators. The voltage across the line unit is 17.5 kV. They given the voltage across the string value in line. Calculate the line to neutral voltage. So line to neutral voltage, that is nothing by root 3. Assume that shunt capacitance between the each insulator and earth is 1/8 of self capacitance. That is nothing but shunt capacitance by self capacitance is equal to 1/8, right? That is 0.125. Then calculate the string efficiency, right? So the given line voltage, first of all calculate the phase voltage by root 3. Then the given K value, K is equal to 1/8, that is shunt capacitance by self capacitance is equal to 1/8, 0.125. Then calculate the string efficiency, that is V1, V2, V3. Otherwise voltage across the string by, so number of discs into nearest to the conductor. So look at the figure, 3 insulators as usual. So K is equal to 1/8, 0.125, and voltage across string, voltage across the unit V3. So not string, voltage across the line unit. Voltage across the line is nothing but conductor. Line unit is nothing but nearer to the conductor. So they given V3 directly, right? V3 is equal to 17.5 kV. So apply as usual KCL at junction A, that is capital I2 is equal to I1 plus small I1, that is V2 is equal to V1 into 1 plus K. We know the K value, that is 0.125, that is V2 is equal to 1.125 V1. Then V3 is equal to V2 plus V1 plus V2K. So we know the V2 value 1.125 V1 plus 1.125 V1 into K. We are getting 1.39 V1. So we don't know the V1 value. That's why, but we know the V3 value. So V1 is equal to V3 by 1.39. That is 17.5 by 1.39. So 12.59 kV. So whenever I determine the V1, V2 is equal to 1.125 V1, 1.125 into 12.59, that is 14.16 kV. Now, so voltage between the line and earth, that is as usual, V1 plus V2 plus V3, 12.59 plus 14.16 plus 17.5, that is equal to 44.25 kV. As usual, string efficiency is equal to phase voltage by number of discs into voltage nearer to the conductor. That is 44.25 divided by 3 into 17.5 into 100, that is 84.28 percentile. Right? Three different situations. First problem, the given K value such that you have to determine V1, V2, V3 such that you have to determine V and then string efficiency. Second problem, the given V1, V2. By using that two values, determine K value, determine V, V3 value and determine V and then string efficiency. But coming to third problem, the given V3 value and K value for such that you have determined V1, V2 and total voltage across string and then string efficiency. So three different situations. And fourth problem, each line of three-phase system is suspended by a string of three identical insulators. Again they given three insulators. Self capacitance C farad, shunt capacitance is 0.2 C to earth and 0.1 C to line. Calculate the string efficiency of system if a guard increases to capacitance to the line metal work, lowest insulator is 0.3 C. So this is the improving methods of string efficiency by using guard ring method. So most of the times they given up to third problems, but sometimes they given methods of improvement, that is guard ring method. So the capacitance between the each unit and line is artificially increased by using a guard ring as shown in figure. We are utilizing guard ring, we have to increasing. First one they given 0.1 C and second one they given 0.3 C. And this one is 0.2 C, they given clearly. Junction, apply KCL at junction. A, here incoming capital I2 plus small I1 dash, outgoing capital I1 plus small I1. So I2 plus I1 dash is equal to capital I1 plus small I1. As usual formulas, V2 omega C plus V2 plus V3 omega 0.1 C, the given 0.1, right? So this is the 0.1. And then we are getting V3 is equal to 12 V1 minus 11 V2. Equation 1. As usual, apply KCL at junction B. Incoming is capital I3 plus small I2 dash. Outgoing is I2 plus capital I2, small I2 plus capital I2. Therefore, V3 omega C plus here V1 plus V2, right? V3 omega C plus V3 0.3 C omega, that is equal to V2 omega C, V1 plus V2 omega into 0.2 C. By using that one, we can determine the 1.3 V3 is equal to 1.2 V2 plus 0.2 V1 taken as equation 2. Substituting the V3 value from expression 1 into expression 2. So that means in equation 1, that is the V3 value. Substitute this V3 value in equation 2, we are getting V2 is equal to 0.993 V1 taken as equation 3. Now substitute this V2 value in equation 1. Therefore, V3 is equal to 12 V1 minus 11 into 0.993 V1, that is equal to 1.077 V1. Now voltage between the conductor and earth, that is nothing but V1 plus V2 plus V3. V1 plus 0.993 V1 plus 1.077 V1, that is equal to 3.07 V1. Therefore, string efficiency 3.07 V1 by 3 into 1.07 V1, so 95%. So as compared the last three problems, we are getting 79%, 68% or 85%, but by improving method, we are getting 95% of string efficiency. Right? So by improving the string efficiency with the help of guard ring or grading of insulators, or it may be longer cross arm. So this is the important problem, that is by using guard ring, you have to improve the string efficiency more and more compared to the nominal values. So like this, we have to determine the string efficiency clearly. So first of all, just observe what is the shunt capacitance and what is the guard ring capacitance. This is the, so link pin to line of the lowest unit increased from 0.1 C to 0.3 C. 0.1C from 0.1C to 0.3C increased. That is the guard ring. This is a 0.1C to 0.3C. So once you have to draw the diagram, then easily determine the K values. So apply the KCL at junction A, junction B, and substitute all these things and determine the V1, V2, V3, V1, V2, V3, then easily determine the string efficiency. Thank you. Next class we discuss about the numerical problems on corona and sag. Thank you one and all.